This video is the final lesson for Chapter 7 for our AP Calculus. It's actually a bit above and beyond what we're supposed to do for the AP Calculus course. We're going to look at a method that kind of complements what we saw with washers. It's just another method for finding volumes that are kind of cylindrically symmetric, and it's called cylindrical shells. And sometimes it excels where maybe doing washers is really awkward with an awkward integration and an awkward axis of rotation, which is actually going to be the case here. If you look at our last two pages of notes, we're going to do the exact same question twice. The first time we'll do it by using washers, which is what we know, and then we're going to switch over and do it with shells. So the shape we're going after is kind of similar to these cake pans here, except ours is not quite as elegant. Doesn't have all the little ripples to it, but it's this kind of cool looking cake. Maybe it kind of looks like this, right? Just big cake like that, not made of wood, but made out of cake. And we're going to try to find the volume, but we are going to do it twice. So the story here says find the volume of this cake pan that is formed by rotating the region above the x-axis and below the parabola. Okay, that's actually the bright red region that you see there around the vertical line. Okay, well that's a little awkward. X is equal to -1. So yeah, the rotation is actually going to be around here. Okay, that's where we're going to rotate. We're not even rotating around the y-axis, which would be bad enough. We're actually going to do, you wouldn't call it a lift, it's like a slide, right? We're going to slide that axis over back 1 unit to x is equal to -1. And the region is underneath that parabola. Yep, okay, I can see the parabola there, and that seems to have an x-intercept at 0 and at 3. And it's above the x-axis. Okay, great. If I do this, I should be able to create some washers. Okay, so I'm going to have these little washers of cake. A little bit hard to draw, but one of them would be like right here, which is a nice washer of cake. And we're going to have to try to find the volume of that washer. That way we can teach the calculus how to go and find the volume of the whole thing. If we can teach it how to do that single washer, then we're set. So that washer's got a big radius and a small radius, but to do that, I'm going to need to be thinking about x values. I'm going to have to think about what is the x value of this spot right there on the washer, and what's the x value right there. And then those are going to be measured to that axis of rotation back here, right, in order to find a radius. Okay, well, I need to rearrange this equation here a little bit. Right now we've got y is equal to, I'm going to actually put the x squared part first, so I've got -x squared plus 3x. That's that parabola. I actually need to think about this as being two separate x functions. Maybe I'll draw one of them, let's draw one of them in pink. Okay, this one here, and then maybe another one in blue. Okay, going like this. So I'm going to have to take this this parabola here and then do a careful little bit of rearranging. So I'm going to have to solve for x, and to do that, I'm actually going to have to complete the square. So this is maybe a good motivation to do integration by shells, because this wash method's not so fun right off the start. I'm already having to do something that's a bit laborious, and that's this completing the square. So I have that. Okay, so far so good. But then my Math 11 teacher would say, well, if you can think of this as being a perfect square trinomial, maybe this could be x squared minus 3x, and then take that middle term, cut it in half and square it. So 3 over 2 squared would be 9/4. Okay. Well, I really just added -9/4 to that story because it's led by this negative sign. So I'd have to add on another 9/4. So I can think of this parabola as being y is equal to the opposite of x minus 3 over 2 squared plus 9/4. That's just another way of drawing out that parabola that's made up of the pink and the blue parts. Now, I'm doing that because I need to separate this thing into the pink and the blue parts. I'm going to have to rewrite it so that it says x equals. And I can do that, but to get there, I'll have to, at some point, take a square root. And I'm going to have the positive and I'm going to have the negative versions. So yeah, I could say, oh, okay, this is going to be like, just swinging this around, I guess I would have y minus 9/4. That's going to equal the opposite of x minus 3/2 squared. Okay, well, I can rewrite that. I can move the negative sign, and I can say, oh, well, that's like 9/4 minus y. Okay, just moving that negative onto it. And then x minus 3/2 squared. And now I have to take a square root, and I'm going to have plus or minus. For that pink branch, when I rearrange that to solve for x, I'm going to end up choosing that smaller option. And for the pink branch, I'm going to end up saying that the x for that one, maybe I'll call that x1, it'll end up being, when I finally solve it there, it'll be 3/2 and then minus the square root of 9/4 minus y. All of this awkward stuff is not even the calculus yet. It's just some algebra getting ready to describe x values. The other x value, maybe I'll call that x2, that blue x value, it would be 3/2 and then plus the square root of 9/4 minus y. So now I can talk about the x values, like right here, that's x2, and right here, that's like the x1 for that washer. A lot of work to get there, right? And now I'm going to have to go and integrate this thing with respect to y, that feels weird all the time, with this slid axis over at -1. Okay, I think we can do this. The answer then, the volume for this cake pan, it's going to be the sum of some dv's. That's my plan. So I'm going to go an integral of pi, and then I'm going to have a big radius that gets squared, and subtract off a small radius that gets squared, and then some sort of d thickness. Okay, so the big radius, looking back at the picture, goes all the way from this green axis of rotation line out to where the blue is. So I can find out the big radius by going blue minus green, right? That should let me figure out how big that big radius is. So I'm just about done, because I'm almost at the point where I can say, calculator, you're up. Figure this out. I'm going to pull a pi out. Now, big radius, for me, that would be, again, the blue, right? So I would put in there the blue stuff. 3/2 plus the root 9/4 minus y, and then subtract off that green axis of rotation. Subtract off a -1. That's going to end up actually adding 1. Okay, that figures out the big radius. I have to square it, and now subtract, because I'm doing washers. And I do this all over again, but now I go pink minus the green. So 3/2 minus, this time it's a minus 9/4 minus y, and then subtract my -1 squared, and then it's going to be a dy for the thickness. Now we'll put the limits on here in a second, but if you're wondering, do I need more brackets? Like, do I have to put, well, actually, I never finished that bracket off. Do I need these brackets that I have in blue and pink? And the answer is no, they're not really doing much. Put them in if you like, but the order of operations seems to be okay without them. Now the dy tells me that y's are in charge, so I have to integrate from the very, very first washer, which actually would start right here at y equals 0. And then my last washer would be way up there at the vertex of that parabola, which just from the math 11 of it, I can see is actually at 9/4. So that's what I'm going to put in here for my numbers here. I'm going to go from 0 for y up to 9/4. That'll be my last spot. And we're done. Leave the pi out of there, and you end up with 45 divided by 2, and then throw the pi back on. So let's before we do this all over again, and maybe a better way, let's just take a look at what we did. We did do some washers. Wow, they were annoying because they were lying down flat, so we had to integrate with respect to y. And we went big radius squared minus small radius squared. And so as I find these radii, I have to subtract first, right, because of that slide. I do the squaring, and then that middle subtraction is because of the fact that we're dealing with washers, because of the fact that this cake has got a big hole in the center, which is unfortunate because now you're missing some cake. It was really awkward trying to come up with the x representations, right? That pink and the blue stuff, just trying to figure out how do I find the x based on a y value. But we did it. We did it. Now, the nice thing about integrating with shells is that if one of them is integrating with respect to y, the other one would be with respect to x. I'd rather integrate with respect to x, so that's kind of nice. And I probably won't have to complete the square either. So it could just be advantageous for that reason. The disadvantage of doing this by shells is that you have never done this before, and it's going to feel a little odd. So here's the cake pan that you've got, right? The cake looks like this, and there's this hole in the center where there's no cake. And the whole idea of shells says instead of cutting it with your knife horizontal, making little washers of cake, imagine plunging your calculus knife in vertically and then walking around the cake and making little shapes that look like this. So there, a shell of cake has been extracted and pulled out to the side. We can think of this whole cake as being made up of those shells. The challenge then will be to come up with the exact dimensions of this shell. And the quickest way, though, to find the volume is to say, well, you know what? If you took that same calculus knife and just cut a little slit in this shell and just rolled it out flat, it would look like a nice little rectangular slab of cake. So there's going to be some distance around the circle. That'll just be the kind of length of the cake. And then there's the height of the shell. Okay, that's like the width of the cake. And then there'll be a little thickness of the cake as well. So as long as we can get that whole thing dialed in, then it's actually not too bad. Now I'm actually going to take this picture, if I can, and kind of drop it right inside here or something close to it. Maybe I'll just kind of sketch it. Okay, see what that's going to look like here. So if I was to sketch that just over here, a little shell of cake, to try to think about what that shell of cake would look like, it looks kind of like this. Okay, this little shell. If you were to make a slice in this cake, you know, so there's the back part of the shell. If you were to go and cut the cake and then roll it out flat, you would end up with this shape that looks like this. The distance along that cake would actually be the circumference of your shell, 2 pi r. And then there's some height to that shell, and then there's some thickness to it. But you can essentially say that the circumference of that circle would be how long this shell of cake is actually going to be. Okay, so now the shells of cake, let's draw one. I'm going to draw a little shell in right here. That's one little shell of cake. It has a radius to it, right? So there's some radius to that shell. When it still looks like a shell, I'm going to cut it and roll it out. There's going to be some height to how big this shell is, and then there's some thickness to it. And what I can do is use the letter x to keep track of which shell we're talking about. So the x equals 0 shell is the very first little shell. It's very short. And then x equals 1 is close by to where I've drawn this. The x equals 2 shell would be there. And then the very last shell, won't be very tall, would be the x equals 3 shell. Okay, here goes. It should be nicer, right? The hard part is just visualizing the shells. But once we've got the shells visualized, this math should be better than the last page. So the volume, it's just going to be some sum of some little volume elements, some little shells. Okay, it's like little soup can labels. That's how you can think of it. And so when we go to find these DVs, you want to be thinking that there's some sort of circumference. some distance around, multiplied by some sort of height for your shell, multiplied by some sort of thinness or thickness. That's all you have to do. And when you do that, it'll automatically create this volume element, and then we'll let the calculus add them all up. So we're going to have an integral. All right. The distance around that shell is the circumference. That's going to be 2 pi times some sort of radius for that shell. We'll get to figuring out what that radius is in a second. Multiplied by the height, multiplied by that thickness. Well, for the thickness, it's just going to be dx. Okay, so x's are in charge, and it looks like we're going to begin at x is equal to 0. That would actually be a shell. I'll draw it in, then I'm going to erase it because it's going to make a mess. But that would be a shell that's like right here, and it's really short, right? But it would be right in there. So that's your very first shell at x equals 0. And then the very last shell would be way out here at x is equal to 3. It's not very tall, okay? So definitely going to be going from 0 to 3. And since x's are in charge, what I need to do now is just write the radius and the height in terms of x's. Okay, that's all I need to do. So let's do this radius first. How big is that radius? It's got to go from this axis of rotation line, which was kind of awkward because it was slid back to x is equal to -1, all the way over to this x value, right? Where we're just calling it like, the x for that. Okay, well, x's are in charge, so it's totally okay to just call it x. And then -1 is that other x value there. All right, so this volume here, we're going to go 2 pi. The radius for that shell, it's just going to be x subtract the -1. So yeah, it's like x plus 1. The radius is 1 bigger than the x value. Let's just see if that makes sense, that the radius is 1 bigger than the x value. Yeah, it is, right? Because x is how far you are from the origin, and then it's one more space to there. So x plus 1 does actually make sense. That is how big the radius is, and that's going to say x plus 1. I don't square anything. Now I multiply by the height. How tall is that shell? Well, that depends on the x value, because of course it's going to be walking along this parabola here. But I know that parabola. The y values, okay, so the height, it's equal to the y value of that parabola. But that's just, we've already been told, 3x minus x squared. So we can put that in as our function of x. Right, you want to know how tall that thing is? No problem. It's just as tall as the parabola is. 3x minus x squared. There, that's the h. That's the r. And then a dx. And this thing's done, right? We'll go from 0 to 3. It's actually a lot nicer as an integral. You could, if you had to, you could do it by hand. I would probably pull the 2 pi out front. And then I've got this x plus 1 getting multiplied onto a 3x minus x squared. There's no reason why you can't just use your calculator. It didn't say you had to do it by hand, but I just want to point out that this is actually pretty nice. I could actually do it by hand. I would simplify first. I would expand that out and say, oh, okay, that's the same thing as, once you expand it out, it's a negative x cubed plus a 2x squared plus a 3x dx. And then you can do your antiderivative. Maybe hang on to the 2 pi antiderivative. It's going to have an x to the 4th in it with a little 1/4 bodyguard, a negative sign hanging around. We're going to have an x cubed with a little 1/3 bodyguard, and then we're going to have an x squared with a little divide by 2 bodyguard, and we'll evaluate from 0 to 3. Done. The answer ends up being, if you keep the pi out of there, 45/2, and then throw the pi back in. So it's the same answer, of course, exactly the same answer as before, but maybe it's a little bit nicer. Never had to do that completing the square. That's never fun, and didn't actually have to integrate with respect to y. Now, the flip side, though, is if washers was integrating with respect to x, then shells will be an integration with respect to y. So, one of them will be nice and one of them won't be so nice. And that's it. That's the end of this chapter for AP Calculus.